Vitamin B3, known historically as niacin, has undergone a remarkable evolution in its scientific and clinical significance. What began as a simple solution to a deficiency disease has blossomed into a cornerstone of modern metabolic, genomic, and longevity science. From the early identification of its role in preventing pellagra to today's cutting-edge research on NAD precursors and anti-aging applications, vitamin B3 exemplifies how fundamental nutrient can transition from essential dietary component to therapeutic powerhouse with systemic implications for human health and longevity. The story of vitamin B3 begins in the early 20th century when pellagra, a debilitating disease characterized by dermatitis, diarrhea, and dementia, was ravaging populations dependent on corn-heavy diets. Researchers eventually identified niacin as the critical factor whose absence led to pellagra, establishing it as an essential nutrient. Supplementation with niacin-rich foods or purified vitamin B3 effectively reversed the symptoms, highlighting the profound impact a single nutrient could have on human health. This early work laid the groundwork for recognizing B3 as more than a dietary requirement. It became a symbol of how targeted nutrition could prevent serious disease and improve public health on a large scale. The next phase in the evolution of B3 was its use as a pharmacologic agent. Researchers discovered that higher doses of niacin could modulate lipid metabolism, lowering LDL cholesterol and raising HDL cholesterol, which provided cardiovascular benefits beyond simple deficiency prevention. Niacin therapy became a widely recognized treatment for dyslipidemia, demonstrating that B3 could exert systemic metabolic effects when delivered in higher, pharmacologically relevant doses. This expansion of B3 from a vitamin to a medicine illustrated its broader capacity to influence human physiology, and it encouraged researchers to explore other metabolic pathways that could be modulated by this versatile molecule. The modern era of vitamin B3 research is defined by the discovery of its role as a precursor to NAD, a coenzyme central to cellular energy metabolism, DNA repair, and stress resilience. NAD levels naturally decline with age, leading to reduced mitochondrial efficiency, impaired DNA repair, increased oxidative stress, and susceptibility to age-related disease. This understanding transformed B3 from a nutrient with peripheral benefits into a molecule central to the biology of aging itself. Preclinical studies using nicotinamide riboside, NR, and nicotinamide mononucleotide, NMN, have demonstrated that boosting NAD can restore mitochondrial function, enhance sirtuin activity, and improve metabolic flexibility across multiple tissues. These interventions have shown promising effects on cognitive function, cardiovascular health, muscle metabolism, and tissue repair, positioning B3 as a therapeutic agent with systemic, multi-organ potential. The therapeutic implications extend beyond aging. Research suggests that NAD restoration may benefit metabolic disorders, including insulin resistance, type 2 diabetes, and non-alcoholic fatty liver disease. Vitamin B3's influence on DNA repair pathways also opens avenues for supporting genomic stability, reducing chronic inflammation, and potentially mitigating cancer risk. In rare genetic disorders such as Werner syndrome, which involve accelerated aging due to DNA repair defects, B3 supplementation has demonstrated the ability to improve cellular resilience and mitochondrial function, offering proof of concept for its use as a targeted intervention against intrinsic aging mechanisms. These findings illustrate a critical transition. B3 is no longer merely a nutrient or a lipid therapy, but a molecular tool capable of influencing fundamental biological pathways. Safety and accessibility have played a key role in B3's evolution from nutrient to medicine. Nicotinamide, NR, and NMN have demonstrated excellent tolerability in human studies, with minimal adverse effects even at doses sufficient to raise NAD significantly. This favorable safety profile makes B3 a practical candidate for long-term interventions aimed at improving health span, complementing lifestyle strategies such as exercise, nutrition, and stress management. Unlike many pharmaceuticals that target single pathways or carry significant toxicity, B3 supplementation acts systemically, supporting energy metabolism, genomic stability, and cellular repair in multiple tissues simultaneously. The conceptual shift in how scientists view vitamin B3 also reflects a broader change in medicine itself, from disease treatment to health optimization. Where early niacin research focused on correcting deficiency or treating dyslipidemia, modern applications emphasize prevention, resilience, and longevity. B3 now represents a model for how nutritional science can inform therapeutic innovation, bridging the gap between diet, metabolism, and clinical intervention. Its evolution illustrates the growing recognition that fundamental molecules, once considered simple nutrients, can serve as powerful modulators of systemic health when leveraged with precision and scientific understanding. In conclusion, vitamin B3 has undergone an extraordinary journey from a deficiency-preventing nutrient to a molecule at the forefront of metabolic and longevity medicine. Its ability to restore NAD, enhance sirtuin activity, support DNA repair, and improve mitochondrial and metabolic function positions it as a therapeutic molecule with transformative potential for human health. By tracing its history, from treating pellagra to improving lipid profiles to cutting-edge applications in aging, metabolic resilience, and genomic stability, we see how a single nutrient can evolve into a cornerstone of modern medicine, exemplifying the power of translating basic nutritional science into systemic interventions that enhance health span and quality of life across the lifespan.